so this is section 8.5. This is on a technique called partial fraction decomposition. So let's look at an integral like this to start with. If we were going to integrate this, it would be easier to do by splitting this up into two fractions or two rational functions. 2 over the denominator minus 8x over the denominator. This makes the original rational function into two rational functions that are easier to integrate. This one's a nice little arctangent, and this one's just a u substitution. There are rational functions where it's not as easy to decompose. You know, decompose meaning break apart this rational function into smaller, easier to integrate rational functions. So that's where partial fraction decomposition comes in. All right? So this technique of splitting a rational function into multiple smaller rational functions is called partial fraction decomposition, because we are writing the rational function into smaller fractions, these bunch of parts of a whole. And this word decomposition just meaning to break apart. So let's talk about this technique of partial fraction decomposition. Now, it can only be used on proper rational functions. So what is a proper rational function? Well, a proper rational function has a numerator that has a degree less than that of the denominator. Remember, the degree is the highest power of x. An improper rational function has a numerator with a degree higher or greater than the degree of the denominator. Now, you might remember these terms from like a proper fraction and an improper fraction. Like an improper fraction would be like 7 over 4, right? That absolute value of that numerator being bigger than the denominator. We do have ways of handling a rational function if it does happen to be improper. We're just going to have to use polynomial long division in order to rewrite it as a quotient plus the remainder over the divisor, and that remainder over divisor should be a proper rational function. But basically, we need it to be proper in order to use partial fraction decomposition. Now, we've got 3 different cases for partial fraction decomposition. We're going to have linear factors in the denominator, repeated linear factors in the denominator, or what we call an irreducible quadratic. These are second degree factors, obviously, because it's called a quadratic, and they don't factor over the real numbers. All right, so a reducible quadratic is one that does factor into either linear factors or repeated linear factors. An irreducible quadratic is something that does not factor over the real numbers. So I'm going to look at these, this decomposition technique with these 3 cases. Okay, so you're just going to have to identify which case it is and then follow that technique for it. All right, so my first example, we're going to expand this using partial fraction decomposition. All right, so we're not integrating just yet. We'll get there. Right now, we just want to talk about the partial fraction decomposition technique. So we have this rational function. Now, we could, like I saw earlier, or like I said earlier, split this up into 5x over the denominator minus 7 over the denominator. That doesn't really help us to, if we were to have to integrate this, that wouldn't help us. So instead, we're going to use this technique. So I'm just going to show you how the technique works rather than trying to kind of explain it. Let's just see it in action and then come back and kind of talk about it. Well, the first thing we need to do is factor the denominator completely. So this is a trinomial, and this factors to where, you have the x's up front here to make your x squared. These two numbers out here need to multiply to be a positive 2 and add up to be a negative 3. So that's why I chose that minus 2 and minus 1. Now, partial fraction decomposition says that we're going to take this 5x minus 7 over x squared minus 3x plus 2. We've now factored that denominator into x minus 2 times x minus 1. This can be rewritten as some constant over x minus 2 plus some other constant over x minus 1. Notice how I broke apart that denominator. So I factored it first, and now this is my kind of formula, so to speak, for partial fraction decomposition. So now I just have to solve this for a and b. Well, how are we going to go about that? There's actually two different ways that we can go about this. We can go about this kind of algebraically by, multiplying both sides by this least common denominator. If we do that, and let's say we multiply both sides by the least common denominator, those will cancel. On this side, the x minus 2's will cancel for this first term, and then the x minus 1's will cancel for that second term. And we get 5x minus 7 equals a times x minus 1 plus b times x minus 2. Now, how to proceed at this point is kind of up to you. I'm going to show you both ways that you can go from here. We could multiply this out on the right hand side, and we get ax minus a, keeping in mind that a and b are just constants, plus bx minus 2b. These x's are going to have to match up. Similarly, these constants, green, it sometimes looks yellow on camera. Similarly, the constants are going to have to match up. So what that means is if I look at this yellow stuff, ax plus bx has to be 5x, and negative a minus 2b has to be negative 7. If I take the x out of that, I get that a plus b must be 5. See, a plus b must be 5. So that gives us that a plus b must be 5, and negative a minus 2b has to be negative 7. So maybe you're having some flashbacks at this point. This is a system of two equations with two unknowns. You can solve this by using substitution, elimination, or matrices. But let's not. Okay? There's an easier way to have to go about this. So instead, let's not do that. Let's go back to this 5x minus 7 equals a x minus 1 plus b times x minus 2 business. We can use a different technique. It's called the Heaviside method, or the Heaviside cover-up method. I'm going to plug in a value for x. Let's pick 1. Now, I didn't just pull that straight out of my butt. I chose 1 for a very specific reason. If I plug in 1 for x, look at what I get. I get 5 minus 7 equals a times 1 minus 1 plus b times 1 minus 2. That's negative 2 equals 0 plus negative b. That means b is 2. Now, what am I doing exactly? Well, the whole thing of partial fraction decomposition is I want to find these two fractions that will add up to be my original fraction. I want to decompose, right? I want to break down this fraction into smaller fractions. So this is what I'm looking for. I want to find these numbers a and b so that, you know, I get this rational function broken down into nicer rational functions. All right, so I'm solving for a and b. Sweet, that means I've already got b. Booyah, halfway there. What do you think is the next number that I'm going to let x equal? Well, I chose 1 because I saw that it was going to zero out this term right here and just leave me with b to have to solve. So the other number I'm going to pick is going to be 2. All right, that's going to be 5 times 2 minus 7 equals a times 2 minus 1 plus b times 2 minus 2. That's 0, just like that was 0. So 10 minus 7 is 3, and then 2 minus 1 is 1. That's just 0. Booyah, a is 3. Okay, we're done. This 5x minus 7, and remember we factored that denominator. The formula for partial fraction decomposition said it was going to be a over x minus 2 plus b over x minus 1. I just found a to be 3, so 3 over x minus 2. B is 2 over x minus 1. Now, if you were to get a common denominator for these two, you'll multiply this one by x minus 1 over x minus 1, and this one by x minus 2 over x minus 2, and then combine these fractions. Guess what you get? Oh yeah, it's this. Oh yeah. So this is that technique of partial fraction decomposition. All right, and again, let's go back to this. These numbers that I chose were not willy-nilly. All right, I chose this so that I would zero out one of those terms and just leave one variable to have to solve for. All right? All right, cool. Cool. All right, let's go look at another one here. This is another one that's going to have linear factors in the denominator. The problem with this one is that this is an improper rational function because the degree of the top, that highest power of x is 3, is bigger than the degree of the bottom. All right. That means we have to rewrite this as a proper rational function. And we're going to have to do this using polynomial long division. All right. So I did this back in section 8.1 as a review of different techniques that we might need, knowing that this was going to have to be used. So we are going to have to long divide the bottom into the top. So we got that denominator on the outside here, and then 2x cubed minus 2x squared. I'm going to fill in this x term with a 0. You don't have to do that. I'm just going to do that just so I have every place value kind of accounted for there. All right, let's start the long division process. What do I have to multiply x squared by to get 2x cubed? Well, I got to multiply it by a 2 and another x. So I need 2x. So remember, in the long division process, is kind of the acronym that you use for long division. Divide, multiply, subtract, bring down, and then repeat. Divide, multiply, subtract, bring down. Right? So I divided, and I did the division here by saying, hey, what do I have to multiply by? But really, I'm dividing this by this. So then the next step is to multiply. So I need to distribute this 2x. So 2x times x squared is 2x cubed. 2x times x, or sorry, times minus x is a minus 2x squared. My next step is to subtract. So divide, multiply, subtract, bring down, and then boop, rotate, or just start back at the beginning there. All right, so my next step is to subtract. Now, because I'm subtracting both of these, I tend to just change the bottom row of signs. And I say that because a lot of students will remember to subtract here, but then forget to subtract here. So subtracting is the same as adding the opposite. So I'm just going to change that bottom row of signs and add. It's the same thing as subtracting. That's 0. Oh, booyah, that's 0 as well. Nice. Bring down the next term. Oh, well. That's just going to be another 0. Right? So 0 times that is just 0. Don't even have to put anything else in there. And then we'll bring down that 1. We're pretty much done. I just wanted to show you that if you needed to bring this down and this wasn't a 0, actually, you know what, we'd be done right there. Because look, that degree of that x right there is smaller than the degree that we started with. Now, if you were to divide, let's take an improper fraction, like say 7 over 3, and write that as a mixed number. That is the same as 2 and 1/3. We know that in mixed numbers, the and here represents a plus. This is the same as 2 plus 1/3. That's because if you divide 3 into 7, it goes twice with 1 left over. This is your quotient plus the remainder over your divisor. I'm going to do the same thing over here. My quotient is 2x. My remainder is 1. My divisor is what's out here. All right, if you were to combine these two fractions with a common denominator, you would get the original rational function that we started with. I have just split it up into nicer pieces. Now it may feel like we're done, but we're not. We're still not done. Especially if we were talking about integrating this, we are definitely not done, because we cannot integrate this. So we're going to use partial fraction decomposition on this sucker. So looking at this one and factoring that denominator, we're going to factor out an x. Those are linear factors. I have an x to the first and I have an x minus 1. So I get those two linear factors. Partial fraction decomposition says that I'm going to decompose this into a constant over one of the factors and then another constant over the other factor. Now, does it matter that I called a over x and b over x minus 1? No. If you put a over x minus 1 and b over x, we will get different numbers for a and b, but we should have the same number above x and the same number above x minus 1 when all is said and done. Okay, so at this point, we need to multiply by, multiply by that least common denominator on both sides to get rid of all these fractions. Here the x's go away. Here the x minus 1's go away. On the left-hand side, I get 1. On the right-hand side, I have a, the x's cancel. I get x minus 1. And then b, the x minus 1's cancel, so I'm left with x. Now we get to pick what we want to let x equal to solve for a and b. So, to get rid of a, let's let x equal 1. This left-hand side, super nice. It's just 1. It's just a constant. So we have a times 0. Don't even have to write that. And then b times 1. That just gives me b equals 1. To get rid of b, I'm going to let x equal 0. Yeah, you can let x equal 0. That'll be 1 is a times 0 minus 1 plus b times 0. Don't even have to write that. That'll be negative 1a equals 1, so I get a is negative 1. Okay, so my original rational function, I had this quotient, let's not forget about that, and then I had this rational function. Okay, both of these were together made up my original rational function. So my final answer is going to be that 2x, don't forget about that one, and then this pink stuff decomposes into a over x plus b over x minus 1. So right here, a over x, b over x minus 1. And I just found a and b. Now this is kind of awkward, writing that plus a negative, so I'm not going to do that. Instead, I'm just going to write that nicer as just a subtraction. So there's my final answer. This 2x came from my polynomial long division, from that quotient. And then this stuff came from my partial fraction decomposition of this proper rational function that we got from the remainder of the divisor. So this one's kind of challenging because you have so much going on. You've got that polynomial long division at the beginning, and then you have to remember to hang on to this part of your answer and decompose this using that partial fraction decomposition technique. Okay, so what would happen if we wanted to integrate this? So far, the first two examples I've done is just been, hey, let's just decompose this into nicer parts, right? So what happens if I want to evaluate that? So if you want to evaluate this integral of this rational function, this was from example 2, right? This one should look familiar. So we decomposed that integrand into these 3. Then we just have to integrate each one of these separately. Okay, well, integrating 2x, no big deal. Integrating this minus 1 over x, no big deal. Integrating this one is probably the most challenging because we just need like a quick little substitution, and maybe you don't even need that substitution. You could even just do that one in your head. Yeah, so decomposing that helped us to integrate this into smaller, nicer chunks there. Okay, so these first two examples really were on linear factors. What happens when your denominator factors into nice linear factors. Next up is what happens when you have repeated linear factors. Okay, so let's look at example 4 then. So what do I mean by a repeated linear factor? Well, this is an example. If I factor this denominator, I get the same linear factor of x minus 3 twice. It's repeated. we have a slightly different technique on how to approach partial fraction decomposition when you have a repeated linear factor. We can't just do it like we did with the linear factors and say A over this, B over this, because they're the same thing. Instead, we have this formula that we're going to have to use. And trust me, this is going to be easier to use than it is to say. This looks really, really terrible. I know, like at first glance, you're like, but it's got a great personality. It's smart, it's funny, it's, you know, it's nice. You take it home to your mom, you know, and show her and invite her over for dinner because it's so nice, right? Anyway, so what this is saying is that you're going to have to use kind of every power up to whatever the highest one is in your repeated linear factors. In this case, it's only squared. So I'm just going to have to use x minus 3 to the first power and x minus 3 squared. If this had been to the fifth power, I would have to have 5 of these. This one, this thing squared, this thing cubed, all the way up to the fifth power. So that's going to help us get, you know, anything up here that's going to have to be like of those, you know, x to the fifth power or whatever else that you're going to need. Okay, so what this means is that we have to decompose my original rational function that factored. So this original rational function here factored into this. So using this formula, it decomposes into A, still A and B are constants, over x minus 3 and B over x minus 3 squared. I'm going to multiply both sides by that least common denominator, just like I did before. This time my least common, and you'll notice my least common denominator is always this denominator over here on the left. Not a coincidence. So in doing that, still sticking with my red for this, the fractions all go away if you do it right. So we get x on the left-hand side, A times x minus 3, one of these went away, and B, both of them went away. All right, so what is going on? We have to start picking numbers for x. You may be thinking ahead, being like, well, I'm definitely going to use 3, because that's going to get rid of A. But how am I going to get rid of B? There's no x next to it. I'll show you. So, like I said, we're going to let 3 be x. In doing so, we get 3 equals A times 3 minus 3, which is just 0, plus B. B is 3. Boom. There's no value of x that's going to get rid of B for you to solve it for A. So just pick anything. But knowing that B is 3, we can plug that in at any point. So I just picked 0. Just pick something. Okay? So in picking 0, this gave me this equation. By plugging in 0 for x, that's 0 equals A times 0 minus 3 plus B. Normally this would be a problem because I would have too many variables. But I already found that B was 3. So I can use that and substitute that in. So then subtracting 3 and then dividing by that coefficient negative 3, I get A is 1. All right, so that means my original rational function will decompose into A over x minus 3 plus B over x minus 3 quantity squared. So this is an example of repeated linear factors. These are different than just regular linear factors. When there's any kind of repetition going on with my linear factors, this has to be set up different from the beginning. All right, let's look at another example for a repeated linear factor. This one's really kind of goofy, but I love it. I'm here for it. And we get an integral too. This is what's called a reducible quadratic, and I point that out because we have irreducible quadratic case that's going to happen in the future in this section here. Okay, so this is the difference of two squares, right? X squared minus 1. That's going to factor into x minus 1, x plus 1. But don't forget about this squared on the outside. So we get not one, but two repeated linear factors. By factoring this x squared minus 1 into x minus 1, x plus 1, this squared on the outside here is for both of these. So this is x minus 1 squared times x plus 1 squared. Both of those are repeated linear factors. This means, I don't think you're ready for this. We are going to have to set this up kind of like two separate problems together. So remember with the last one, we just had the what was it, x minus 3 quantity squared. And we had a over x minus 3, b over x minus 3 squared. I'm going to have to do that twice. I'm going to have a, b, c, and d. A and b, and then c and d. Yeah, it's a lot. It's just going to be really tedious to have to do here. So we've got the a and the b are for my repeated x minus 1 linear factor. And then c and d are for my repeated x plus 1 linear factor. Okay? All right. Whew! All right, so by now, you kind of know the routine. Once we get this set up from whatever formula we need to use, be it the one for linear factors or repeated linear factors, now we have to multiply through by that least common denominator. I know this looks like a hot mess, but yeah, it's just me multiplying each and every term by this denominator and canceling what can be canceled. It will get nicer after this step, but for now I realize that this step looks like hot garbage. So multiplying through by this x minus 1 squared and this x plus 1 squared, every single one of these, here we get the x minus 1 cancels one of those x minus 1s. The x minus 1 squares completely cancel. X plus 1 cancels one of the x plus 1s. Here the x plus 1 squareds completely cancel. And that's what I'm left with. So you can see I'm trying to color code this so that you can kind of follow along with where some of this came from. All right, let's start plugging in numbers for x. I started with 1 because I saw that plugging in 1 would eliminate, this x minus 1 term. So if I plug in x equals 1, this is a constant over here, that's just 1. That's going to be a times 0. I didn't bother with 1 plus 1 is 2 squared is 4 because that 0 is going to the whole term. 1 plus 1 is 2. 2 squared is 4. 1 minus 1 is 0. Who cares what everything else is? That's gone. 1 minus 1 is 0. That term's gone. So just from plugging in x equals 1, I get that b is 1/4. All right. There's b. I still have a, c, and d to go. How about we plug in -1? Right, that'll get rid of some of the other terms. So by plugging in -1, that's going to eliminate the a term, the b term, and the c term. So that'll give me that d is 1/4. Yeah, it's weird that we're getting fractions for these, but that's okay. It happens. You can get positive, negative fractions, you know, it happens. Okay, so we plugged in 1 and negative 1, but there's nothing else that's going to eliminate any of these. Now is where we have to revisit our substitution elimination. So remember in the very first example, I said, hey, we could match these up and use substitution, elimination, or matrices, and I was like, oh, let's not, because we don't always have to. This is one of those cases where we're able to find 2 of the variables, but the other 2 are not going to be found using this technique. So here's what we're going to have to do. So coming back to this, I just rewrote it on this page here. I'm just plugging in 0. That's a nice number to have to plug in. You can pick any number you want. I guess if you wanted to pick x equals 14, you could. I just plugged in 0. And that gave me this equation. I already had b and d, so I just plugged those in. So by plugging in for b and d, and then simplifying that, so we know that that 1/4 plus 1/4 is a half, and then subtracting that half over, 1 minus this half is 1/2. That gave me this equation for a and c. In order to solve an equation with 2 variables, you need 2 equations. You need the same number of equations as you do variables to solve it. So let's pick another number for x. I just went with 2 this time. I didn't want to pick 1 or negative 1. I've already used those. So I plugged in 2 up here for x. And I got this. Again, plugging in for b and d. And then just doing some of these computations. Adding that together gave me 10/4. And then subtracting that from 1 gave me this equation. I now have to solve these 2 equations together using substitution, elimination, or matrices. I chose to use elimination. I don't know how familiar you guys are with that, but I'm happy to refresh your memory. So we have this first equation, this negative a plus c equals 1/2, this 9a plus 3c equals negative 3/2. I chose to multiply both of these equations by 9 because I'm thinking, okay, if I add these together, that'll eliminate my a. So multiplying that by 9 gives me negative 9a plus 9c equals 9/2. Adding those 2 equations together, I get 12c equals 3. Adding this together, I'm going to get 6/2, or just 3. Dividing both sides by 12, I get c equals 1/4. I can then back substitute into either one of these equations to find a. So c being 1/4, I just back substituted into this equation. I could have picked either one of them to find a. Alright, so that means that I finally have my numbers for a, b, c, and d. That means my decomposition for my original rational function is a over x minus 1, b over x minus 1 quantity squared, c over x plus 1, d over x plus 1 quantity squared. We still need to integrate this. Now, notice how when I rewrote it with the integration in there, how I changed it a little bit. This is the same thing as if I just pulled that negative 1/4 out front, or if I wrote it as negative 1 and then 4 times x minus 1. So I just rewrote it a little nicer. All right, so boom, 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 boom. Each one of these integrals here. Ooh, okay. Ooh, we've seen this one before, right? That one was a natural log of x minus 1. So that one's going to be a natural log of x plus 1. This is the one that might be a little bit challenging we just have to use a u substitution. We're going to let u be x minus 1. That'll be a 1 over u squared, so that's going to be a u to the negative 1, or sorry, u to the negative 2. When I integrate it, I'm going to get u to the negative 1 over negative 1. And then substituting back in for my u, and then because it's to the negative 1 power, it's going to move down. And then this minus right here, boop, came this. Now over here, you may be like, how did you do this one? It's the exact same thing. I just didn't write it because it's just going to be u is x plus 1, and then du is dx. So we're going to have 1/4 the integral of 1 over u squared du, which is u to the negative 2, and that'll be again negative 1/4 u to the negative 1. Exact same kind of substitution there. So that's why I just didn't write it again, because I was like, oh, it's going to be the same thing. Just my u is going to be x plus 1 this time. Okay, so I'm going to end the video here. This is the first part of partial fraction decomposition. So this finishes up the linear factors and the repeated linear factors. We still have irreducible quadratics to talk about. This is a super long section, and I'm really, really sorry about that. So I didn't want to put it all into one video. Okay, so the next video will be the irreducible quadratic examples.